not sure if I was able to find it, but I'll just share. I can share a link right now. Give me a sec. Okay, so I think we'll just get started. Well, maybe people join halfway and they'll figure it out. So I shared a link to today's notebook, and I think Sarath shared it on his website, but you can always follow along at home, and I guess I would encourage you to have it open so that you can maybe play around with the code as well. I think it's a lot easier to understand what's going on when you can actually interact with what's going on. So we're going to be going over a small tutorial on PyTorch today, which you will be needing for the next assignment. Mostly just the basics, so you shouldn't have to learn too much about it, but everything should be covered today so that you'll have all the tools necessary for the next assignment. Assignment 3, that's going to be on, I think, active critics and policy gradient methods. So why do we want to use PyTorch instead of sticking with, for example, NumPy, which we've been kind of using this whole time, or NumPy? So PyTorch, a small introduction here. It's a Python package that provides kind of 2 high-level features. First, it allows to do tensor computations. And that, in a way, you can just think of it as what NumPy is already providing. So allowing you to do array multiplication and operations, basically. Except this time, PyTorch will allow you to do all those operations on a GPU. So basically, it'll do everything that NumPy can do, but you can put it on GPU, so it'll be much faster to run. And the other thing is that PyTorch offers a lot of deep machine learning functions, kind of convenience functions, such like that you don't have to write everything from scratch every time you implement any kind of neural network. So there's a small introduction on tensors here, but really it's just the same thing that you've been, same thing as NumPy arrays, just they're going to be called torch.tensors instead. And there's a bunch of, high-level components that PyTorch is usually used for. So of course, there's a torch component that's mainly going to contain all the basic operations on tensors like NumPy has. Torch.autograd, which is typically very useful to calculate gradients, which you usually need when doing neural network stuff. Torch.jit, we won't be touching that, and you won't need it, but it's just a compilation stack that allows for faster code. But we won't talk about that today, nor will you need it. So you can just ignore that. Torch.nn is this neural network library that Torch offers that's kind of offers a bunch of pre-written code for a bunch of stuff in neural networks. And torch.multiprocessing we won't need as well. And torch.utils is just kind of anything that doesn't fit in the other categories. So any utility functions that Torch might have written for you. Good. I guess just want to make sure anybody who has a question, you could just write in the chat and I'll try to answer it as soon as I see it. But I think you can also just unmute yourself and stop me whenever you want if there's ever a question. So again, we're just going to focus on the Torch library, torch.autograd, and torch.nn. So Torch is just going to be a reiteration of everything that's NumPy. Just instead of writing np.whatever, it'll be torch.whatever. Torch.autograd, the gradient stuff that you will need, and torch.nn is just a library of neural network blocks. Let's go ahead and start by installing a few things that we might need. The thing about, we don't have to install PyTorch because the Colab notebooks usually always come with PyTorch, but we will install these 2 libraries that help us just to visualize some stuff. You don't actually need these if you don't want them to use them during the assignment. It'll just help us print and visualize stuff that we need. So we're going to go ahead and install, just import a bunch of stuff that we need. Matplot.pyplot as PLT. This is something you might be familiar with because of assignments. It'll just help us plot. OS, just give us the libraries of operating system commands. time Colab files. Lets us import stuff from the file navigation system in Colab. This is the thing we just installed that helps us print stuff, NumPy as usual, and all the Torch things that we might need. Good. We can check what version of Torch we have installed. So the number here is the version of Torch, which is 1.12.1 is the latest version, so we're all good on that. And here, this plus CU113 is the CUDA binary that you have supported. And really, it's kind of you have to install a version of PyTorch, and you have to install the right version on top of that that supports the current GPU that you have. In this case, CU113, CUDA 11.3 basically is the GPU version software that we have on the Colab cloud. If you want to run it on your own GPU or something, you might have to make sure you just have the right binary implementation on top of the version. If you didn't get the right one, you can always install it. Good. And you can run this command on your terminal whenever you would like, just to make sure there's a GPU available somewhere. Here we can check what GPU is available on our cloud service on Google Colab, and you can see that there is one, name and info and a bunch of stuff, information about it. Don't worry too much about it. Basically, there's one available here. Okay, so we have everything installed, imported everything we need, and let's start by doing this. Sorry. Let's start by playing around with some tensors and see, how you can handle them and what they do really. Okay. 1 second while I set something up here. Is everything clear so far on PyTorch and what it does and why we would need it instead of NumPy? Okay, I'll take silence as a good thing for now. So we have a setup, and let's just start by playing around with some tensors. So, let's go with this. Okay, so this is one way to initialize. We're just initializing a 0 tensor. If maybe you probably familiar, that's kind of analogous to the numpy.zeros method. It'll just initialize a 0 tensor. And you'll see that if you start printing this tensor, just like you would a NumPy array, it's going to look very similar to how NumPy arrays are formatted and displayed. So we've kind of initiated a 0 tensor with dimensions 1, 2, and 3. So just to make sure, you can do tensor.shape, and you'll see that this is indeed what we got. Here I've specified what device I want to put it on. So that's kind of a difference with NumPy. And I've specified CPU. I'll go over the devices a little bit later, but for now, we're just going to pretend we're still going to be working on CPUs. But you can always initialize it on GPU. And if you want to make sure, they always have a device property to see what's going on, what device the tensor is on. So we print out the one on CPU, it's on CPU, and on GPU, it's going to be on GPU. We'll cover GPUs a little bit later and just some details about how exactly you would handle GPU operations. It's not very complicated, but for now, we don't have to worry too much about it. And one thing that might be convenient to know is that you will be working a lot, for example, maybe converting things from list to NumPy arrays and NumPy arrays to tensors or vice versa in every direction. So how would we be able to do that? Because you'll see that if you do something like Python list 1, 2, 3, and then obviously tensor with zeros, and you try to do an operation on this list with tensor, you're not really going to get things that you might expect to get. So what's more convenient is always doing operations within the same realm of stuff. So NumPy arrays, NumPy arrays, tensors with tensors, and lists with lists. Sometimes it might work. Like you might be able to make a NumPy array and do operations with a torch tensor, but it's always better not to leave things to chance and not let the system itself figure out the conversion that you maybe want to do. The implicit conversion is not always correct. So this torch.tensor is very similar to numpy.array. Whatever argument it'll take, it'll kind of implicitly convert whatever is in there to a torch.tensor. In this case, I put a list, and it's able to do it by itself. Right, so if I go from here, we have the tensor that just contains whatever is in that Python list. I could have also made a numpy list and done the same thing. And see that this torch.tensor is kind of a do-all function that'll take anything as an argument and convert it into a tensor, whether it's a list or a numpy array. Okay, and then there's a couple of other ways though to convert a numpy array to a torch.tensor. There's also this from numpy thing that'll do the same thing. Again, we go like this, and again, we have the right information. So there is, however, a detail here on what is the difference between torch.tensor.numpy array and if you do from numpy. If you test it out yourself, for example, we'll just take this little block of code. Okay, anyways, if we take this here and try it out just to see why is there maybe a difference between from numpy and torch.tensor. So here I've initialized a list. I made it into a numpy array. I'm going to use torch.tensor on that numpy array, and I'll use torch.from numpy for that numpy array. And then after doing that conversion, so we already had the tensored version of those numpy arrays. We're going to do some in-place operation on the numpy array, the original one that we've used to create the tensors. And we could print everything. So our numpy array, of course, is no longer 1, 2, 3. We've changed the first index to 100. So it's 100, 2, and 3. The second version, the torch v1, however, still has the original version of Python list. So it has 1, 2, 3. And v2, you see that it has a different value. And this is because when you do torch.from numpy.numpy array, it'll share the memory from whatever it used to create. So torch, tensor, v2, and numpy array have a shared memory. Every time you change anything in numpy array, it'll implicitly change the tensor v2 because they're getting the information from the same place. That makes sense. So that's just something maybe to watch out for. I guess the safer thing and maybe more intuitive to most would be to just make sure you always use torch.tensor, unless there's some reason you might want to use this and have a shared memory. It's a little more efficient, I guess. I don't think you'll ever be in a situation where you run out of memory, though. So it might cause confusion. Okay, so we can make tensors. And next, let's see what we can do to these tensors in terms of machine learning stuff. So let's start with a linear regression example. We've created a kind of test data set here. So torch.arange. And by the way, don't be afraid to just Google every time you want to know how to do something or like what a method does. Torch has a pretty good documentation. I think if you just Google PyTorch, for example, arange, and because you don't know what it does, you can always check the documentation here. If you don't know, you can always do help. And it'll print out kind of everything that was already on the website. This one looks a little bit nicer maybe sometimes, but if you don't want to change tabs, don't be afraid to use the help function and abuse of it every time you want to know how to do something or you don't know what something does. Arange is basically just the range method that in Python. Just it'll create a torch tensor instead of a Python list. So we're creating a dummy data set with X values is this, and Y values. You can print out what we just did. So X is just kind of these range from 0 to 10. And Y is our labels, our test labels. And we're kind of doing a binary classification task here. If anybody's familiar, I think maybe if you took the machine learning class, you might already be familiar with all this. But basically, we're going to be taking this as an input and trying to predict the class given by Y, the corresponding Y. It's a lot easier to interpret by the image. So given the X's, we have these data points. Everything from 0 to 5 needs to predict a class of 0, while everything from 6 to 10 will give a class of 1. This is just some dummy data set we've created to test out some stuff on PyTorch. So we're going to do linear regression by starting out with some weights and bias variables. If you remember, linear regression will have kind of this hat of Y going to be defined by our X variable times T plus B. Our X is given, it's our input, and then we have our weights, like our model in this case is just represented by the weights W and B. This is just a simple linear model. So we're going to try to predict the classes by taking the features X, multiplying some linearly by some weights and with some bias term B. We initialize those terms with 0. This is kind of what we're doing here. And actually, we're going to wrap the whole thing by a sigmoid because we want to make sure that our outputs go from 0 to 1. If you don't know what the sigmoid function is, it kind of just squeezes everything between the space of 0 and 1. Is that good? Obviously, if we take our current values where weights and biases are 0 and do predictions on them, it's not going to give you much. They're all just going to give 0.5 on the sigmoid function. And our actual predictions, we'll see that given whatever input, our predictions are always 0. Right. So haven't learned anything yet. This is just an initialization of a model that's always going to spit out 0 for your class label. WOV, we have a very simple model already. And of course, the accuracy is not very good. It's about 55%, which is about as good as random in this case. Okay. Still, let's not keep going. Assume maybe most of you already know a lot of this stuff. And maybe are just here for the PyTorch stuff. So I won't go too much into the details and the nitty-gritty of what's going on with this classification task, but we have to define a loss function. So a loss function is kind of telling our model how off you were, like how correct you are, right? This is the function we're going to minimize, try to minimize on our model. We're defining a cross entropy loss. The cross entropy loss the binary cross-entropy loss will intuitively, pretty much, if you have all the correct ones, it'll give you a 0 error, while if the more incorrect labels you have, the higher loss you have, right? So by minimizing this loss, you'll have a more and more accurate function. And what we need to do is calculate these terms. So just to reiterate what is going on here, we're setting up a dummy problem and trying to do linear regression on it. And you don't have to worry too much about all this, but basically I'm showing how we would do it without the torch library, basically, like the stuff that's in autograd or torch.nn, and how we would do it by hand. And by the end of this exercise, you'll see that it gets quite annoying to do linear regression even, which linear regression is quite simple, but it gets quite annoying to do that by hand. And then we'll see how much easier it is when you can use Torch to handle all of that. So if you can't understand too much of what's going on here, don't worry, because you won't be using it for the assignment, right? Everything will be wrapped. This is kind of the back end of what's going on in Torch that you will be using. But the goal is to find these derivative terms. These terms, the derivative of the loss with respect to all of your parameters. Actually, this should be a B here. And how do we find these terms? We've initialized the terms. And how would one go about to find these two terms? Well, without any libraries, you would have to take this loss function and do yourself the calculation of what exactly is DL, DW, and sorry, this is supposed to be a B, and DL, DB. And we're lucky here, we only have two parameters, right? W and B is just sized 1 and 1 here. But imagine if you had like a 4-layer neural network with a bunch of different activation functions, and maybe you're doing some crazy other stuff in that neural network, and then you're going to have to calculate the gradient, and then you're going to have to calculate the derivative of that loss function that you have with respect to all of your thousands of parameters. That's just not something that's very tractable. And you can see how that gets really annoying. It's going to get really annoying here with just 2 parameters. But we have to do this ourselves. So what's DL, DW? We're going to have to take the derivative of this loss function with respect to the weights W. If you guys want, you could try to calculate it by hand, but I'll write the answer right here. I think you're just going to have to take my word for it, that the derivative of this function with respect to the weights is just the input x times the predictions, the output of your function, minus the true label. I mean, DB is a similar process. This is the prediction, so it's that linear prediction here, y hat, minus the true labels, and then we take the mean of that. Okay, so we have a function to calculate the gradients, no matter what input we have. And what we can do now is apply the gradients with gradient descent. We take some learning step size of 0.001. Our weights are W and B. Given the gradients, we can take a step by doing W minus the step size times the gradient. If you're familiar with linear regression, this shouldn't be anything new to you, but basically this ensures that we're going toward taking a step towards a loss function that is going to be smaller, so a more accurate model. So is everything still good? I guess. Okay, let's put everything in the one place. We initialize our basically we'll initialize our model by initializing the weights. We can make a prediction with the model given the inputs, right? This is how we've defined our model. It's W times B times X, the input, plus B and we wrap it around a sigmoid. Once we have the predictions, the actual labels out of that is whether if it's bigger than 0.5, it'll be 1. If it's smaller than 0.5, it'll be 0. That's because we're doing binary classification. And we can calculate some accuracy based on our predictions. This is just as a metric to see what's going on. We can initialize our gradients. We calculate the gradients, right? That we figured out the formula ourselves analytically by doing that derivative. With the gradients, we take a gradient step, and then we get a different value of W. So here it is. Here is kind of putting everything we've written so far in one cell, which is doing literally just one step of gradient descent. So let's clean things up a bit. We're going to put them all into functions so that we can reuse them whenever we want. What we need to do, remember, we need to initialize our parameters of our model. We need some way to compute the prediction of our model given the X and our parameters, W and B. This get labels thing is pretty much just kind of a helper method on top of the predictions, but it's just doing some post-processing on the predictions to get the actual labels. Accuracy is not something you need for gradient descent, but it's just a metric we'll use. Then you need a compute gradient function that takes in everything, right? The input that you want to compute the gradient with, the parameters to your model, and the true label of your data set. Good. Then we just put it all in one function. And you need some way to apply the gradients, right? So given your weights and given that you calculated the gradients, how do you update your gradients? How do you update your weights based on these gradients? In this case, we're doing a very simple gradient descent step. So now we have to write a training loop because we've only taken one step, right, of gradient descent in that previous cell. And what we want to do is take many iterations of that to get a good model. So let's go over what's going on. I've set the seed. We're setting some hyperparameters to our model here. So like just some constants that we need to define ourselves to the gradient descent. In this case, the learning rate is how big of steps you want to take for a gradient. And then you have other stuff like your weight initializations, right? We have init params. We're going to just initialize some logging stuff, and we're going to write our iterations here. Basically, we're going to repeat this process here a bunch of times to iterate our gradient descent, and then we're going to plot what's going on. So we've done 2,500 steps of gradient descent on this, and we can see that our accuracy is getting better over time. So it's working. That's a good sign. This is the kind of curve that you want to see. Usually it's a lot smoother than this, but because we only have 11 data points, it looks like this in this example. Basically, when you know that your thing is working, typically the loss, this is on the y-axis, the loss is going to, this is the accuracy. So the accuracy in this case is going to go up, but the loss is actually going to go down usually. So we just plot that. You can see I have a loss. This is the typical thing you would want to see on your loss function. Does that make sense for everybody?
Yes.
Thanks. Good. So still, there shouldn't be anything new here. We haven't used anything about Torch, really. Like, we're using tensors, but there's no difference here between these Torch tensors and NumPy array. Basically, we haven't taken advantage of anything. But obviously, you can see that it gets, writing all these things every time can get annoying. I've already talked about this a lot, but the hardest step really that you really don't want to do usually is doing this calculation, right? I've given you the answer here. I don't know if anybody's actually tried it, but it's not always the funnest thing to do derivatives on your loss function every time you want to do gradient descent. So how can we streamline this process so that, first of all, it'll be less prone to errors because you won't make maybe an accidental mistake on the gradient calculations. It's not just that, right? Like things like you have to keep track of your weights yourself, right? Like you have W and B every time. Like what if you have a big neural network? Are you going to input your entire parameter space every time and keep track of that yourself every time? Once you have the gradients, you also have to take a gradient step, right? We've done a very simple gradient descent, but let's say you want to do something more complex than that. That's not something you probably want to write every time either. So one by one, we're going to start replacing all the functions we wrote into PyTorch and see how much easier it'll be once we have the PyTorch backend on top of this. So the first thing we'll do is replace this compute predictions. Basically the forward, what typically people would call a forward pass, because what you want to do is a forward and a backward. But and we'll see how we can do that using PyTorch. We're going to be handling all the parameters. We don't have to do it ourselves, though, the linear function. So PyTorch will have a big library of a bunch of already pre-written computations for you. In this case, we'll use, this is pretty much a linear application of the weights onto X. So that's what linear does. I think that's be transposed. Right, so this line is replacing this because they've already, Torch already has a package for doing linear operations. And here we'll keep doing sigmoid for that. Actually, sigmoid, here we could have written ourselves. I think it's like something like 1 over exponential of the E, but we're using the package. Okay, so here, not too different. We can make sure that we haven't messed anything up here. That these two things are equivalent. Right, compute predictions and compute predictions v2. Good, no assertion errors. Okay, and next thing we want to do is replace the gradient computation. Right. Actually, I think we missed one thing, that we want to replace the loss function first. So given our predictions and the true label, let's calculate this loss function. Sorry, so we've actually already written this, but this is how we wrote it before. And why? And we can see that there's no need to write this loss function yourself because Torch already has a version of this on binary cross-entropy predictions. Why? And we can make sure here that we haven't messed up our own implementation of binary cross-entropy. We'll assert this that we didn't make any error here. Nice. Okay, so we had the right implementation, but obviously there was no reason to risk writing the wrong implementation because they already have it implemented in PyTorch. We have our loss function, we have our prediction, and let's see if we can do our gradients. How can we compute the gradients? How do we do that in PyTorch instead of this way here? This is how we wrote it. How can we do it now in PyTorch? So a really nice thing about PyTorch is this autograd package that I talked about earlier. And autograd will basically automatically compute the gradients of any output you have. So like the output is here, compute predictions, right? We're gonna pass our input towards our model. This you can think of as like a forward pass, right? We're gonna put a forward pass, and the input X will go through our model in the forward direction, so like kind of in the direction you'd expect things to go into your model. You calculate the loss, so the thing you want to calculate the gradient with respect to, right? In this case, it's just the binary cross entropy loss. And then to calculate the gradients, it's as simple as doing loss dot backward. And that's why we call this the forward pass now, so that when you take the gradient, it'll go backward. If you're familiar with how automatic differentiation works, and actually, if you're familiar with backpropagation through time, backpropagation, the algorithm, if you took the ML class, maybe you'll have a better sense of why this is called forward pass and backward. But basically, this loss dot backward method is implicitly doing the backpropagation computations to calculate the gradients. And you'll notice that this thing actually doesn't return anything. Like this won't return the gradients. They actually get stored into your tensors into this dot grad field, right? So all tensors might have a dot grad field, and whenever you call backwards on these given tensors, like on a loss that has these tensors as an input, it'll populate the field of their gradient, of the tensor's gradient. So this doesn't return anything, but you can check what the gradients are in the dot grad field. Good. Let's test this out. Again, we have the weights. And then we're gonna basically write this down here. So we have our weights. We're gonna compute the gradients with our old method, and let's compute them with our new method on PyTorch and just make sure that they're equivalent. Actually, this will give a wrong thing. I don't think it'll work. And there's a reason why, right? So it's going to give you an error here. Element 0 of tensor does not require grad and does not have a grad function. So why is that? What does it mean that it doesn't require grad? When you do dot backward, it actually is going to calculate the gradient with respect to all the inputs that all the tensors that it has an input. So like W, in this case, X and B, and even Y, because Y is an input to loss, right? But in reality, we don't actually need the gradients with respect to Y, for example. We don't need the gradients with respect to X either. So it would be a waste of time for the machine to calculate the gradients with respect to everything every time, right? So you have to specify which tensors you want to actually calculate the gradients with respect to, which is what we're going to do here. That's why it's complaining here. We haven't specified any. We haven't told him to do any gradients with respect to any of the tensors. So it's doing loss dot backward, and then there's no input with respect to do any gradients with. They're sort of complaining about not having anything that requires grad. So the quick and easy fix to that is to just set these variables to true. Right. Once you set this to true, do this here. You can check it yourself that the requires grad field is set to true, right? W is set to true, but for example, X doesn't have requirements to do gradients. So given that, once you complete the lost dot backward, it'll populate the field of dot grad for any tensor that has requires grad equal to true. Every tensor that has requires grad equal to false, it won't compute the gradient width. So you have to make sure, you know, that that's all specified correctly. So now we can probably do this and make sure that, there you go. We've done the exact same computation here, but instead of using, you know, instead of calculating the derivative yourself and implementing those formulas yourself, you just do a quick dot backward and you're done. And we've just checked, it gives the same gradients. So that's great, right? Like we can have as complicated as an operation as we want here. We can have lots is equal to some crazy neural network of W, X, B, whatever, Y. It could have a million different parameters. It could have a million operations. At the end of the day, as soon as you call dot backward, it'll calculate all the gradients with respect to everything that requires grad equals to true, and it'll just give you the gradients automatically. So you don't have to do any of the gradient computations yourself. So that's great. And if you're interested in kind of learning more about how that's done, you can look into backpropagation. That's more of the theory of what's happening. But implementation-wise, it's called automatic differentiation. And most of these machine learning packages have some sort of implementation of that in order to compute gradients. A really great thing. But it all happens under the hood. So if you're not interested, you know, just pretend this is some black box thing that will calculate gradients for you. That's all you really need. So let's try it again. But this time with the things, sorry. So here we're going to do it again with all of the functions we wrote ourselves. So no PyTorch really. Again, the loss goes down, everything's working. But let's do it now in PyTorch. So what was the difference between here and there? I'll go over the optimizer in a little bit, but basically the optimizer takes the role of apply grad, right? Apply grad here. We haven't written a proxy for that yet. So that's what this is going to do. The predictions and accuracy are the same functions. What we do here is a new optimization step from the optimizer. And the new here is just doing dot backward instead of doing compute grads, right? So this should be clear. We've already gone through that. There's nothing new here. But what's happening in the optimizer and how is that replacing our apply grad, right? You'll see that the function is the same. So we're actually doing the same thing. So under the hood, optimizer is going to define some way to update your weights given gradients. Optimizer.step will take in all the weights that you specified with respect to optimizer and do some kind of update with respect to the grad field of W, right? This is why we don't have to go like W and then grad as an input to optimizer. Sorry, EW, because they're all implicitly defined earlier. When you define your optimizer, you have to tell it what it wants to optimize. In this case, we want to optimize parameters W and D. And then along with that, you have a bunch of parameters maybe of your function. In this case, we just have learning rate. And when you take the optimizer.step, it'll take whatever the parameters it has, you gave it as an input, and take a step of a gradient step, basically, depending on what optimizer you specified. So in this case, we're doing SGD, but really it's just GD, but it's the same thing. We're doing the entire data set. But yeah, like you specify what parameters you want to optimize. And then instead of calling apply grad, you can just do optimizer.step to take a step in the right direction with your gradients. This implicitly uses, right? So do the learning rate times w.grad. So this is what it's doing under the hood. Again, we've kind of abstracted a lot of things here, right? We don't have to do gradient We don't have to calculate the gradients, nor do we even have to keep track of the gradients. Like there's nowhere in here to even see the term dw anymore, right? Like dw or w.grad. It's all handled by itself and doing everything neatly on PyTorch. The other nice thing is that, you know, you might be wanting to use different optimization methods as just gradient descent. So you can feel free to look at the library, but there's other stuff like the atom, which is probably the most popular to use. That'll give you different ways to update your gradients. Cool. So now we've kind of replaced most of our things with PyTorch. And again, it's the same thing though, right? We haven't changed anything. We've just changed the way we compute the things. So overall, there is a way to handle this every time, right? Like some sort of recipe is emerging out. There is a procedure to doing this every time you want to optimize the model. This procedure is going to look like this, basically. You always want to initialize your parameters, basically initialize your model somehow, right? And then you want to initialize your optimizer with respect to your model, right? And then you do your training loop, and in your training loop, there's kind of these steps that you're always going to be taking every time you do any kind of optimization in PyTorch. You're going to compute the forward pass. Forward pass just means you give your input through your model. You have to do this reset grad thing, which I'll get to in a bit. But let's just ignore this for now. You have to do a forward pass. You have to compute the loss with respect to your forward pass. And then you do dot backward on your loss, whatever you want, whatever loss function you want to optimize, you want to minimize, you just call dot backward on that. And then you want to update your parameters optimizer at a step. And then you just repeat this loop every time, right? Create your model, create your optimizer, and then your training loop is do forward pass, compute the loss, do a backwards pass, which is just as simple as dot backward, and then do a step to update your parameters by doing optimizer on a step. And what you want to do with this, why do we have to reset the gradients every time? Why is that? So if we go back here into our replacing our gradient things, every time you call dot backward here, it's going to calculate the gradients with respect to the thing you've called backwards to, and then populate the field. But it doesn't replace the gradient that's there. It's always going to accumulate gradients. So in this case, for example, we have w.grad is negative 1.13, right? If I run this again, you might expect this to be a different value, but we have this here. Yeah, there's an assertion error because our thing is different, right? So remember, one pass of the backward gave you negative 1.13. Right, this is just this multiplied by 2. Every time you call that backward, it just adds the gradient to the grad field. So if you already have some gradients there and you never reset it to 0, it's going to keep accumulating gradients, which is not really what you want usually. It's back. And that's why you need to make sure every time you do the training loop to reset the gradients. You can do this by doing optimizer.0grad. There's other ways. I think you can explicitly do something like dot grad is equal to 0 or dot 0 grad even on this weight thing. There's a bunch of ways to do it, but this is probably the easiest way. Just make sure, always remember to call optimizer.0 grad to reset your gradients back to 0. Okay, yeah, something that people may forget, and it's going to ruin your gradients if you forget to do that. But this is a good recipe to follow. Initialize your model, initialize your optimizer, forward pass, reset grads, compute loss, compute grads, update params. These lines of code you can pretty much copy paste every time you do any kind of learning, deep learning, supervised learning at least, right? Okay, so we've kind of covered everything that is to cover in the basics of PyTorch. So far, we have seen how to train basic models using PyTorch. However, there are some other things that we want to cover as well to make it even more convenient. First of all, how to use GPUs, which I told you, I promised that I would cover. And the second thing is we're still handling weights in a kind of old-fashioned way, where again, we have to keep track of our parameters of our model ourselves, right? Like our model here is defined by this list of weights W and B. But there's something you want to avoid. You want to avoid having to keep track of your model yourself, especially when things get complicated. So we're gonna see how we can do this better and take advantage of, in this case, this is going to be using torch.nn library. NN stands for neural network. Okay, so let's continue on to this. How do we use GPUs on PyTorch, and maybe cover some of the pitfalls that may happen when you use GPUs on PyTorch? First and foremost, every time you write a script or a notebook or anything that you want to use GPUs, I would recommend to always start your notebook. So like I would recommend to put this all the way at the top of the notebook as soon as you know you're going to be using GPUs. If it's not a notebook, then you're writing your script, your Python script or whatever you're using. Just define your device that you want to use, right? In this case, torch.device CUDA 0. It's because we have a CUDA-based GPU, and 0 is kind of the indexed, like which GPU do you want to use? Almost every time, just write the string and it's good to go. Like, as long as you have a GPU, CUDA colon 0 will give you the first GPU on the system, which is almost always fine, right? Unless you guys want to use multi-threading and do some more complicated things with the GPUs. But this line, you can copy paste at the top of your script, at the top of your notebook every time to define your GPU device. If you want, you can also define it as the CPU, if you want to use CPU. But I would always recommend defining your device whenever you want to use PyTorch, even if you don't want to use GPU, just explicitly write CPU. It's not necessary because by default it'll be CPU, but you know, it'll avoid any potential mistakes if you want to switch devices. Once you have a device defined, let's just make some random tensor here, a 2x4 tensor. Make another 2x4 tensor, and let's check what device they're on. Right, I didn't specify anything here, and by default, it's always going to put it on CPU. So if you don't do anything, even if you have GPUs available, all of your tensors and everything will be done on CPU. So how can we put it on GPU? We've already kind of done it a little bit before, but let's do it here again. It's as simple as putting it to the device. And in this case, we define device as the CUDA 0, right? So now if we print out which device our tensors are on, tensor 1 is on a GPU. Tensor 2 is still on CPU because we haven't put it anywhere. And then let's try to do an operation with these two tensors. And intuition here is that you might notice something go wrong. You're going to get an error here. Expected all tensors to be on the same device, but found at least two devices, CUDA 0 and CPU. They even give you an exclamation point because it's, I don't know, a bad error, I guess. Every time you would do operations, any kind of torch operations, this includes plus, minus, multiplication, anything more complicated like a linear layer some loss function like the binary cross entropy loss, right? Torch will not be happy if you try to do it on devices that are not on tensors that are not on the same device. So you always have to make sure that your tensors or everything that you input in Torch to be on the same device when doing operations on them. Otherwise, it won't work. So let's try this again, but this time we make sure that our second tensor, we put it on GPU as well. And this worked fine, no error. We got our no error. And on top of that, you'll see that the output of that is going to be automatically on GPU. I didn't have to specify here and put it on the device. Just because, right, there's no need for that because all the inputs are already on GPU and you know for sure that they're always on the same device, always, right? Like moving things from GPU to CPU is a whole thing. So by default, it's going to stay on the same thing. Does that make sense? So it's quite easy, right? To find your device at the top of your script. And every time you want to put things on GPU, make sure you do to device. And the detail here to make sure that you don't mess up something is that you always want to make sure that every operation you do are always on the same device. Don't worry too much about it, I guess, because if ever you forget that, it'll just give you an error. And the error is pretty clear. So you shouldn't run into that problem. Like if you run into it, it should be an easy fix, and because you know exactly what happened. Okay, so we've covered GPUs a little bit here. Let's go over defining models in torch.nn. We're going to define a simple neural network here with a bunch of, so here I've kind of initialized a bunch of parameters of our neural network: batch size, input dimensions, output dimensions, intermediate dimensions. I've created some random input and some random target, some random y and x. This is just an install. Again, it's very similar to the ice cream package. It's just to visualize our models, you know, in a nicer fashion. So we're going to import that to make sure we have it. And let's start by making a feed-forward neural network with these parameters. The easiest way to define models in Torch is with this nn.sequential object. nn.sequential, and if you want to know more about it, again, don't be afraid to just Google or ask help on this to find exactly what's going on. There's tons of documentation on PyTorch. It's a very popular library, so a quick Google should give you the answers every time. But basically, this inherits the nn.module class, and it'll create some model with a bunch. It's not so clear here, but the arguments of this basically is you can put a sequence of Torch modules in it, and it'll sequentially process all of those modules as your model, right? So the easiest way to make a model is by calling this nn.sequential, and as an input to it, you put your other submodules. We're talking about a 2-layer feed-forward neural network here, right? So the first thing to do in the sequential is you do a linear application, a linear layer. A linear layer, remember, is very simple. It's kind of what we've already done previously. Onto your input dimensions, and you have to specify input, intermediate dimensions on your linear layer. And then after that, we sequentially apply a sigmoid to it. This is the activation function, if you're familiar with with some machine learning. And then after that, you do another linear layer. So here we specified a 2-layer neural network that first applies a layer with size intermediate dim. It's going to apply a sigmoid over it, and then it's going to apply another linear layer with output dimensions specified here. And the important thing, again, is to do to device. Remember, we were talking about putting tensors to device? Well, actually, you should also be putting basically anything that's an nn.module let me just. Oops. Anything that's an nn.module class, you can also put it to devices. And this will implicitly put the whole thing into the GPU, which includes all of its parameters and basically all the tensors in there, right? So we can print out what this looks like. We have our first layer that goes into 150 dimension, sigmoid, and in our third layer that goes from 150 to 200. It'll print a bunch of stuff. You can already see how many parameters we have in this little neural network. So, it's good. We don't have to manage these parameters ourselves, right? It's all contained into this simple model object. So that's one of the easier ways to define models in PyTorch. Alternatively, you can, if you have some more involved operations, you might not want to just simply do sequential operations. Maybe you want to define some other functions on top of your model. Maybe you want to keep track of other things, right? So if you want more fine-grained control over your model, you can create your model yourself using the NN module subclass. So the NN module subclass will always have to define two things at minimum. First, your initialization, and then a forward function. And the forward function is kind of just the forward pass of this model. What this model will do when you give it an input. So, we've defined a simple model here. We can do the same thing. Layer 1. And you can give a bunch of parameters here, right? Like I could put input dim here, so that way I can make a class here that will initialize any kind of model. But for now, let's just keep that simple and not have that. And layer 2. We define all the layers, all the modules we want to define, and an initialization method. Cool. And then in forward, we have to specify what we want to do whenever we get an input with these, right? So out layer 1, self layer 1 x, out self dot sigmoid x, and return self dot layer 2 x. You can see why we used sequential earlier, because this is just the sequential applications of all the layers we initialize here. Okay, so there is an array here on top of the dimensionalities of the layers. Let me just try to figure out real quick. Should have been out here, and here should also be out. Good. We defined the exact same model as the one that was here, except in a little more of a convoluted way. But you might notice that this is a much more flexible class to use when you want to make models. Right, like actually, you can parameterize this any way you want with input dim and output dim, and you kind of define a general function for any kind of two-layer NLP in this way, right? And when you specify, when you create your model, you can do input dim. Right, like I can use this class to make a bunch of different MLPs with different dimensionalities in whatever layers. If you don't want to, though, you don't have to use it this way, and you can just keep making models sequentially this way as well. It's just as good, simpler even maybe, so you might be less prone to errors. So that about covers everything there is to cover, I think, that you might need for the assignment. You know, we've covered how to do gradient descent with Torch. Always remember, you know, I would just go over the cell and take this recipe and kind of copy paste it wherever you need, every time you need to do stuff. The GPU stuff, right? Make sure that they're always on the same tensor, same device, and there's always a better way to handle models within the torch.nn. And at the end of this tutorial, I put a little bit of a thing for you guys to try. So the notebook that I gave to everyone, right, that you all have access to, doesn't have the answers to here, right? So I'm kind of asking you guys to implement it yourselves. But this is a small example of putting this all together and training a simple neural network on the MNIST task. And if anybody's familiar with the MNIST task, it's just a classification task of these digits that's used for benchmarking very often. It's just a big data set of these little handwritten digits. And the neural network is meant to take each of these little images as an input and output what digit it represents. So it'll take this picture, 0, and say this is 0, 1, 2, 3, 4, or whatever, right? So I've set up an example here on training a neural network on MNIST. So this will kind of put everything together. You guys could try it out to make sure that everything is understood properly. Most of it is already written. All you need to do really is to fill in those gaps that correspond to the recipe of PyTorch learning, right? So remember, initialize a model, initialize your optimizer, you compute the forward pass, you compute the loss, reset the gradients, compute the gradients, and then you take a step. This really should correspond to pretty much like one line each, and then that's done. It's like 5 lines of code, and you've trained your first neural network, I guess, if it is your first one on PyTorch for the MNIST dataset. There's still 20 minutes left to the tutorial, so I'll give you guys, if you guys want to try it out right now, some time to try it, and I'll be here if you have any questions while you try it. And maybe like, if anybody's interested, I can also give the answer on this code and how you can write the code to how you can complete this code. Is that good?
Yes.
Okay, great. So if you don't want to try it out now, or if you have someone else to go, you can feel free to leave. I'll be here for the next 20 minutes. I'm also holding office hours right after this. I know probably some of you guys have questions regarding assignment 2. So if you would like to stick around, actually, it's going to be in a different call, but I'll be in office hours after this. But I'll stick around for the last 20 minutes for you guys to, if you want to implement this and you have questions. And if anybody's interested, I can also just go over this right now. But yeah, thanks for coming for the tutorial. And I hope this was informing enough for you guys to move on to the next assignment. So just out of curiosity, is anybody trying this right now and they would like some time, or does anybody just want me to go over it right now?
You can just go over it, I think.
Sure. Okay. Okay. So let's initialize our model. Just going to go ahead and find where to do this here. Okay. How do we init our model? We're going to init our model the same way we did here, the sequential thing. So let's go ahead and just copy paste this little box here. I'm going to have to call it model. So the trick here, I mean, the tricky thing here is to just make sure that you have all the dimensionalities correct, right? Like you saw the error I had earlier. If somewhere it doesn't match properly, you're going to get problems. In this case, I believe the input dimension should be number of features here. And then the intermediate dimension, you can put whatever you want. This is something that's outputted, like the hidden layers, basically. We're gonna go ahead and just use a ReLU activation, which generally is probably the one that works overall the best and is easiest to use. Well, we're gonna define some hidden layer here. It goes 256 to 256. And we'll do another activation function on this. We're going to do another layer to get to the output dimension that we want. So everything in between, you can do whatever you want, as long as you match like here to here and here to there. Like if this is 128, this needs to be 128, right? If it's 256, this has to be 256. The thing you have to make sure is that your input and output dimensions are correct. So the input to your neural network is whatever input dimension you have for your problem, in this case, number of features. The output dimension is, again, problem specific. In this case, we're talking about a classification task. So the output dimension, we're going to tell it to output 10 different classes, like a 10-dimension output.
Sorry, just a small question. Is the number of the number of neuron or parameters getting bigger? Like, is it getting smaller to bigger, or is it wiser to go the other way around?
Really, there's no wrong answer to that. It can go smaller to bigger, bigger to smaller. It can go bigger, smaller to bigger to smaller, right? I can go 512 and then 512 here, and then I can even do another layer here. That'll go from 512, 256 to 128 or something.
Okay.
Generally speaking, I don't think you guys have to worry too much. It'll just be, honestly, I would just keep them all the same size. I don't think you're going to be working with two big networks. But maybe generally speaking, it goes from small to big to small. If that makes sense. Yeah. Because usually the number of features is smaller than the hidden dimensionality. It's like 10 or something. You get to a big hidden space, and then at the end, you have to go back to a smaller one, right? So it makes sense to go from small to big to small.
Yes. Yes.
Just one layer here that we have to specify as well. Because we're doing a classification task, we're going to wrap our linear, because the linear layer can output any kind of output, right? Like there's no bound on the answer it can give. Intuitively, for this classification task, we want it to give a probability, basically. So if you have 10 classes, every index of your output represents like the probability of it being one of the classes. And that's why we're doing softmax. Softmax is kind of a nice way to handle probabilities, because it squeezes any kind of input tense vector into one corresponding one that has that corresponds to probability distribution. Like the sum of it will be equals to 1. That's what this is doing. We've initialized our model. Good. Next thing to do, remember, in that recipe is to initialize an optimizer. The first argument to optimizer should always be all the parameters you want to optimize with respect to, right? In this case, it's as easy as calling a model dot parameters. And then I think learning rate was already specified somewhere, I hope. Maybe not. Oh, it's here. Yeah, learning rate. And then you so this is mandatory every time you initialize an optimizer. Always remember to put which parameters you want to optimize. And then usually all of these, sorry, I'll just do with SGD. All of these optimizers have a bunch of different parameters as well. They can specify. In this case, learning rate. If you use something like Atom, it's going to have learning rate, like momentum, maybe epsilon, whatever. Typically, you can just worry about the learning rate, and all the other values, just keep them as default, and it's fine. Good. So we've finished. Now we've created our optimizer. I'm going to use the Atom optimizer because I think I know it's going to give a better model in this example. So we've initialized everything we need to do. Now we just need to write our training loop. Remember to compute the forward pass. The forward pass, you just do it by calling your model function onto your input. Your predictions, the model, basically it'll take whatever input and pass it through your, however you define your model. That's done. You have to compute the loss. The loss function was actually already defined for you. Maybe this is something you're going to have to do as well usually, right? Define some kind of loss. I think it's always going to be given for you guys, maybe, or in the policy gradient, you might have to define it yourself, and that might look like the policy gradient theorem, which will give you the expected return as the loss you want to optimize over. But you have to define basically some metric you want to optimize over. In this case, it's going to be loss function. You give your predictions, your X train, Y train. Done. This is just some for logging purposes. Always remember to reset your gradients before taking a step, right? Right before computing the gradients, make sure you reset the gradients. Reset, compute the gradients for log plot backward. And then you take a step with optimizer.step. And that should be done. So you've written everything. We can test it out on the MNIST problem. You can see that we got an accuracy of 97% on the training set. And again, you can see the loss going down like a typical loss curve you'll always see. If you don't see something like this, something probably went wrong, basically. Accuracy of 97%, that's pretty good. If you want, we can try it out and visualize exactly what this looks like. So PLP show here. Diary shape 8x8. Oh, shape. Sorry. Okay, so like for example, this. Honestly, I would even have trouble recognizing this digit, but we can see, for example, what our model thinks of that. Let me make sure that there's not something wrong here. X train 0. Oh, here, let me just put everything and let's see what the output of that model was. Okay, so our model, sorry, gave doesn't writes a probability distribution over all the things. Actually, it looks like it's very confident that it's a 1. Basically, if you just go like this. Oops. Yeah, remember, don't do NumPy stuff on torch.tensors. Yeah, so our model thinks this is a 1. which I guess probably correct. Maybe if you look at something else, yeah, this is clearly a 4, and you can just visualize yourself that your model is working pretty well. So I think that about covers how you would train the MNIST with the PyTorch stuff. Again, I guess I would recommend maybe trying it out yourselves later, because the notebook I gave doesn't have the answer to this cell. So it would be a good exercise to just do it over yourselves again, just to make sure you understand the basic formula for training any kind of neural network with PyTorch. I think that about wraps it up. Is there any question or any concerns or questions that you guys might have? Otherwise, we can end it here.